Thanks. So I'm going to be talking about proton-boron 11 fusion. Now that's different from the fusion energy that you generally hear about, which is deuterium-tritium, and I'm going to be making that distinction. But we are after a societal problem, which is the future of the world's energy needs. I've just put down this picture over here, which appeared in the Princeton website when we got some funding a couple of years ago from ARPA-E. And it says that we received funding for unlikely, fantastic clean energy technology. That's all true. It is very unlikely. It is fantastic if it works. The one thing that may not be entirely true is the received part, because I was part of the $200 million that got rescinded by Trump from Princeton University. But that's another story. We're doing great research. One thing that I should say, appearing in this picture, is my team: Ian Oakes, Elijah Combs, Mikhail Modik, and Tal Rubin, former graduate students of mine or present graduate students. Normally, my modus operandi is to send students away once they get the degrees, and that's what I've been doing for the last, well, I'm on my second millennia. But we were looking at some basic physics that just seemed to have enormous implications, and that's what I'm going to get into right now. Okay, and so we decided to start Pale Blue. Now, there's no question that there's a grand societal challenge, which is the need for clean energy, and it's only being accelerated by our needs in AI right now. The holy grail of fusion energy is proton-boron 11. I learned in graduate school that it doesn't work, so we shouldn't be paying too much attention to it. The mainline fusion, which is hard enough, is the deuterium-tritium reaction. You see here deuterium and tritium forming a fusion reaction, and then you get neutrons and helium out. Tritium fuel is very rare. It's poisonous. It's radioactive. And the neutrons make the whole machine radioactive. Although it's much cleaner than fission, it is a proliferative technology because of the technologies involved. As opposed to that, proton-boron 11 is the reactants: proton, that's just hydrogen; boron 11, 80% of our boron is boron 11. It's cheap. It's in the detergents. It's completely plentiful and non-radioactive. And the reaction gives you three helium nuclei, which is also completely non-radioactive. The question is whether it's going to work. And in that regard, we have a new approach. Instead of putting everything in a soup, which would be requiring much higher temperatures, this is what we learned in graduate school, will not make it work. We take advantage of the fact that proton and boron are very different masses, and therefore you can keep it far from thermal equilibrium. The whole point is to make the traffic control laws work to your advantage. We have 30 peer-reviewed publications, 4 years of theoretical research, and a number of patents to prove it. Our near-term strategy is to get the science straight, and then the rest of it, the technology, the regulatory approvals, the market risk, all that is going to be so much simpler. Thank you very much.
I'm curious, materially, what will this then do?
What?
Like, for everyday society, what will this then accomplish?
Well, every society is energy challenged, and the world is energy challenged. We have to solve that problem. And as we develop new technologies like artificial intelligence, or for that matter, airplanes, anything, we need to have more energy. So this is a societal problem. People fight wars over it. We hope to have the next generation of energy source.
What's the biggest challenge you're trying to overcome right now?
The biggest challenge I'm trying to, well, these are theoretical challenges, okay? What I was saying is that we're going to make the innovation is to keep the reaction far from thermal equilibrium. In other words, we don't put everything in the soup and just heat the soup to a very high temperature. And we don't want to confine everything. We want to confine some things and not other things. Because when we already produce the helium, we need to get rid of it very quickly. So there are a couple of very important physical problems that rely on what I'd call traffic control. So you have to direct the traffic, obeying the traffic laws. Traffic laws are first and second law of thermodynamics. There might be a couple of other laws too, but we really need to obey those laws on thermodynamics, and that's what we try to do.
Okay.
Did that answer your question?
To a certain extent, because that's theoretical, but how do you do it on the lab bench scale? I mean, what are you doing to accomplish this?
Yeah.
At this point, we are coming up with innovations on a theoretical basis. We think that as opposed to the rest of the world, which is building bigger and bigger fusion machines and seeing whether the technology can work, we're more confident of the technology because we're not going to be radioactive, we're not going to have to produce tritium, we're not going to have to do all those things that are very expensive, and you have to build big things to make sure that they work. Rather, we're seeing theoretically, at least for the next 2 years, then I'll tell you what we're going to do after that. But for the next 2 years, we want to make sure on paper it's going to work all the way. And once we have that, I think people will become very, very interested.
Okay, thank you.
So is your team the only team that's working this proton, what is it, boron? Wait,
Yeah, proton board.
proton boron 11, thank you. Read it wrong.
There are other teams. They are not pursuing this differential confinement approach that we are, in the sense that from the beginning, we're deciding, let's not put everything in a conventional nuclear reactor like a tokamak or a stellarator. Let's build the kind of reactor that will confine just the boron and the protons, but not the helium, for example.
Okay, just because, two comments on this, because number one is, I'm sorry that you got your money rescinded, but I would hope there'd be other labs out there who might be feeling or thinking similarly, where there could be some leverage. You know, they have something, you have another thing. And then the other thing is, I think it's funny, you're the pale blue fusion. I think you need to get with the blue lab folks over here about climate, because I think there's a good voice out there.
Oh, yeah, right. Actually, pale blue, we picked that name, PB, pale blue, and then it's Carl Sagan's pale blue planet.
Exactly.
Yeah.
Yeah.
I'm sorry, was there a question that you had for me?
No, but it was just saying a comment, because earlier, I don't know if you heard, but it was the blue lab folks who talk about climate control and
Right.
getting words out, et cetera.
Right, we want to save the planet too.
Yeah.
Yeah. I will depart from script just a little bit, if you permit me. Okay, and that is that, yes, one societal challenge is energy. There's something very special about the proton boron 11 approach, and that is that it's absolutely clean and non-proliferative. And I'd like to call your attention to 1985, the Reagan-Gorbachev summit, which is when the United States and Russia decided to build a fusion reactor called ITER. And this was going to be something, they couldn't agree to do something that was proliferative, like fission, but they could do, I know I got 30 seconds, okay. They were able to agree on that. Now, $65 billion later and 40 years later, they're still building it. However, proton boron 11 would be less proliferative by far, and my dream is to put it in Neom. Neom is this new Saudi Arabian city, very close to Israel, and this would be the perfect device for the Abraham Accords. So that's my other dream on this particular topic. Thanks.
Thank you.